Hello again, students. So, this is the second in the sequence of videos on the law of cosines. And we have two tools right now. We have the law of cosines, we have the law of sines, and we really have one other tool. We know that the angles of a triangle must add up to 180 degrees, or pi radians. So we can use those three facts to solve a triangle. If I give you three facts about a triangle, then in general, not always, you can determine all of the sides of that triangle. So let's do it. Let's talk through this. So I won't actually solve these triangles. I'll instead give the ideas to do that. So in the case of a side-side-side triangle, such as that depicted to the right, you can use the law of cosines together with some inverse trigonometry to figure out each individual angle. So let's explain how. Let's write down, I won't finish it, but let's write down what we need to do to find A. Well, I can use the law of cosines centered at A. So the law of cosines says that the side opposite A, 2, squared, should be equal to the sum of the squares of the two remaining sides. That's what it would be if this were a right triangle, if A in fact were the right angle, but it's not. Instead, you get 2 is equal to 4 squared plus 3 squared minus 2 times the product of those two side lengths times the cosine of A. Neato. So there is exactly one unknown in that equation. It's A, which is what we want to know. So I won't go through all of the walk of doing all of the arithmetic of isolating what. You know what? Why not? I got time. Let's actually find A. So let's do that. Let's put A on the one side. So I guess I'll take all of this and add it to the other side. I'll subtract that to the other side. I'll get 2 times 4 times 3 times the cosine of A is equal to 4 squared is 16, plus 3 squared is 9, minus 2 squared is 4. I got space in this line. 16 plus 9 is something you've added up enough times that you should just know that that's 25, minus 4 is 21. So 2 times 4 times 3 times the cosine of A is equal to 21. So that means that the cosine of A is equal to 21 divided by 2 times 4 times 3. 21 is a multiple of 3, and I see a 3 in the bottom, so I should expand out that 21 as 7 times 3 divided by 2 times 4 times 3. The reason to do that is so that you can cancel the 3's. And what are you left with? You are left with 7 over 8. So the cosine of A is 7 over 8. And let's think about this. So what are the solutions to cosine of A equals 7 over 8? Well, one of them is cosine inverse of 7 over 8. The other reference solution is 2 pi minus cosine inverse of 7 over 8. But think about what cosine inverse is. Cosine inverse is an angle that is somewhere between 0 and pi. Those are the angles that you're allowed to see in a triangle. This quantity, on the other hand, is in pi, comma 2 pi. That's not allowed. And in fact, none of the other solutions are. None of the other solutions will be between 0 and pi. So this is the only solution to that equation, so I know what A is. A is cosine inverse of 7 over 8. And you know what? Just for laughs, let's go ahead and compute that using a machine. Inverse cosine of 7 over 8 is somewhere around 0.505 radians. If you want that in degrees, right, you just need to multiply by 180 and divide by pi. Somewhere around 28.96 degrees. Groovy. So hopefully that felt pretty natural. And in fact, do you think you could do something similar to find the remaining angles? Of course you could. I don't have space here. You could do the same walk to find B and C, and then you could even walk with a checksum. A plus B plus C should be pi. Nice. Next, a side-side angle triangle. And we saw this a little bit last time. This is an ambiguous case, and let's draw a picture of why it's ambiguous first. So let's draw the picture of why. So I know that I see an angle of pi over 3. I go out a distance of 2. And then I don't know what angle this one points out at, but I know how far to go. I know I should go out a distance of 3. So I'll draw, centered at that point, a circle of radius 3. Let's see, 3 is bigger than 2, so I guess it'll look something like that. So, I don't like where I drew that line. It's too suggestive. So I'll draw that line of at the angle of pi over 3. Oh look, it intersects the circle in that point. So that must mean that's the triangle. But there are other things that could happen, right? So in this case, this will be a unique solution. Let's see what would happen if I flip that. What if instead, what if this were 3 and this were 2? What if I asked you to solve that triangle? Let's do that same thing. So I have this angle, pi over 3. I go a distance of 3. And then I'm going to draw a circle of radius, 2. It looks like this arc intersects this in 2 different points, and I see 2 different triangles which both satisfy the conditions. There's one triangle that has an angle of pi over 3, a side of length 3, and a side of length 2. I guess this color. Here is another triangle, and let's see if it satisfies the same things. Well, it has the same side of length 3. It has a side of length 2, a different side of length 2, but the same side length. And it also satisfies this pi over 3. So there are 2 solutions. But there's another thing that you can see happen. So it's possible you draw this circle that you need to. Maybe that line doesn't intersect it in any points. You might see no solutions. And let's see what happens in exactly this case. Let's try to count the solutions to this, to determine the solutions to this equation. To this triangle, sorry. And here's how we'll do it. So let's think about trying to find the angle A. And, well, let's see. There's the angle A. Oh, I should erase some things here. So it looks like the law of sines should be useful. So the law of sines will say that the sine of A divided by 2 is equal to the sine of pi over 3 divided by opposite pi over 3 is 3. And I know what the sine of pi over 3 is. The sine of pi over 3 is root 3 over 2 over 3. That's root 3 over 6. And now I'll multiply this 2 over to the other side. Sorry, that's the wrong way to do that. I'll multiply this 2 over to the other side, giving me sine of A is equal to 2 root 3 over 6. That is root 3 over 3. So at a glance you would say, well, there should be like 2 solutions that seem valid. One of them is arcsine of root 3 over 3. The other one is pi minus arcsine of root 3 over 3. This one will be in the interval from negative pi over 2 to pi over 2. But notice the angle can't be negative. It's an angle inside of a triangle. So it'll be somewhere between 0 and pi over 2. Pi over 2 is a right angle. This will be an acute angle. This one, on the other hand, pi minus something between 0 and pi over 2 will be between pi over 2 and pi. So this will be an obtuse angle. But one fact you should remember is if a triangle has an obtuse angle, then the side opposite that obtuse angle will always be the biggest side in the triangle. But look opposite A, you see 2. Is 2 the largest side in that triangle? It is not. So, the obtuse solution is not allowed. There's only one value for A. A equals inverse sine of root 3 over 3. And now that you know that, well, how can you find the angle C? Well, the angles have to add up to pi radians. So, compute C by doing some subtraction. To find the side length A, you can use the law of sines again. Bangarang. So next, let's try to figure out how to solve a side angle side triangle. So, to determine this side length is straightforward. That's the law of cosines. Right, that'll tell you c squared is equal to 4 squared plus 2 squared minus 2 times 4 times 2 times the cosine of pi over 3. And that's easy to solve, so I won't even do it. So that's how you can find the other side length c. Now look at those two angles, a, and little c. So we'll use this same logic. So remember, the issue when you use the law of sines to find an angle is that there might be two different options. The angle might be acute, the angle might be obtuse, and if you don't know any better, you might report only the acute solution when the obtuse solution could work. Well, remember, an obtuse angle, if it exists in a triangle, must be opposite the longest side. Well, let's look at A. The angle A is opposite the side length 2. Is that the longest side length? It's not, because of the angle, the side length 4 is bigger than the side length 2. So, you can use the law of sines to get A, right? Because you write down sine of A divided by 2 equals sine of pi over 3 divided by c, which you now know. Right, it's that you just computed it moments ago. So now all you need to do is use some inverse trig. The only thing left is the side length c. Find the side length c by using that the angles of a triangle add up to 180 degrees or pi radians if you prefer. Finally, if you see a triangle in which you know two angles and a side, I don't care which two angles, I don't care which two sides, you can solve that triangle by first finding the remaining angle. Right, you know that a plus pi over 6 plus pi over 6 will be pi. Solve that for a. Right, the angles inside of a triangle have to add up to 180 degrees or pi radians. Look at context to tell if you're in radians or degrees. So step 1, find a. Now find those remaining side lengths. Using the law of sines. That's the easiest thing to do. You could find one of them with the law of sines and the other one with the law of cosines, but I think that option would be mildly more difficult. Nice. So there's some strategies. Let's use this to solve one particular triangle. I will focus on this, a side-side-side triangle. So you know those three sides of this triangle. Let's find the angles alpha, gamma, and beta. And if this were an in-person class, here's what I would do. I would say, I'm just going to shut my mouth. I'm going to break you guys into three different sets of students. And those three different sets of students are going to compute the angles alpha, beta, and gamma independently. And then as a checksum, we will see if they actually add up to pi radians or 180 degrees if you want to walk in degrees. Since I can't do that, I'll talk through the first one in detail. Then I'll pause the recording and I'll give you the solutions and I'll talk through them quickly without writing them. And then we'll do this checksum. So let's get started. Let's find the cosine of alpha. So if I want to find the cosine of alpha, let's use the law of cosines centered at that pair. So the side opposite the angle alpha is 4. 4 squared is 6 squared plus 3 squared minus 2 times 6 times 3 times the cosine of alpha. Right, so that last bit is like the error term. It's how far the Pythagorean identity is from being correct for this triangle. Sorry, Pythagorean formula. Solve for alpha. So 4 squared is 16. Now I need to subtract this to the other side. 46, oops. Minus 3 squared is 9. Equals negative 2 times 6 times 3 times the cosine of alpha. Cool, so let's carry on from there. So I know what I'm going to have to do. I'm going to simplify this, and then I'll divide this over to the other side. Then I'll use inverse cosine. So let's do that. 16 minus 36, well that's 36 minus 16 would be 20, but it'll be negative, so that'll be negative 20. Minus 9 will be negative 29. Then I need to divide this over to the other side. Divided by negative 2 times 3, 2 times 6 times 3. I know it's the same as what I wrote. I'll try to respect order. Is equal to the cosine of alpha. So now you want to simplify that fraction, but there's not much to do. Negative divided by a negative will become a positive. 29 is prime, so I know that there's no canceling I can do. 29 is not even, I can't cancel the 2. 29 isn't a multiple of 3, so I can't cancel the 3. So that, now I should just compute out what the bottom is. Let's see, 2 times 6 is 12. 12 times 3 is 36. So 29 over 36 is equal to the cosine of alpha. And I know that the angle that I want is going to be between 0 and pi. And that's exactly the range of inverse cosine. So this alpha is the result of inverse trigonometry. Alpha is the inverse cosine of 29 over 36. And there's the exact answer. Let's find some decimal approximations. Using a machine, that angle alpha is approximately 0.634 radians. And, well, there's an approximate value. Let's also get it in degrees. 0.634 radians is approximately the same as that number multiplied by 180 divided by pi for an angle of 36.34 degrees. Again, approximately. So for emphasis, these are both approximate values. Nice. Let me tell you what I will do next. So we can do something very similar to find the remaining two angles. And so I think there's no point in going through that in all the detail with you right now. So here's what I want you guys to do. I want you guys to walk those out independently. I'll do the same. I'll write up my walk and we'll talk through it pretty quickly. But on the count of 3, pause the video and we'll come back. 3, 2, 1, pause. All right, here we are. We are back. So let's walk this out. So find the angle beta using the law of cosine. So the law of cosine centered at beta, color-coded. There's the side opposite beta. It says that 6 squared should be equal to 4 squared plus 3 squared minus 2 times 4 times 3 times the cosine of beta. Doing some arithmetic, hopefully without mistake. Subtract the 4 squared, which is 16. Subtract the 3 squared, which is 9, to the other side. 2 times 4 times 3, let's see, 2 times 3 is 6, 6 times 4 is 24. Okay, I had to do that. We do that because I can't do arithmetic. You wind up with, on the left-hand side, 36 minus 16 is 20, minus 9 is plus 11, divided by negative 24, gives you negative 11 over 24 as cosine of beta. So beta must be the inverse cosine of negative 11 over 24, and you'll notice there that I say that that is an obtuse angle. Why is that an obtuse angle? Well, let's draw it. If you want the inverse cosine of that negative number, there's the unit circle. There is this negative x value. Remember, the range of inverse cosine is that bit of the unit circle, angles between 0 and pi. So it looks like this angle must be that. Yeah, that angle is obtuse. It's bigger than 90 degrees. So, approximating it, beta is about 2.05 radians. That's bigger than pi over 2. And in degrees, that is about 117.28 degrees, which again is bigger than 90 degrees. Similarly, to find the angle gamma, use the law of cosines. So the angle gamma, there's the angle gamma, there's the side opposite. So the side opposite, 3 squared, should be equal to 4 squared plus 6 squared, minus that error term, 2 times 4 times 6 times the cosine of gamma. So that should mean 3 squared is 9, minus 4 squared, that's 16, minus 6 squared, that's 36, is equal to negative 48 times the cosine of gamma. Doing that arithmetic, 9 minus 16 minus 36 is negative 43. Divide that by negative 48. There's the cosine of gamma. There's no cancellation, right? Those two don't have any common factors. So gamma is the inverse cosine of 43 over 48. That's 0.48 radians, or about 26.38 degrees. Now, let's check if these actually add up to pi or to 180 degrees. And I'll do this 3 different ways in order to emphasize the danger of only saving approximate values. So let's use the totals in radians first. So alpha plus beta, did I say degrees? I meant radians. Plus gamma is apparently approximately 0.634 plus 2.05 plus 0.46. Let's see what that adds up to. That adds up to 3.144. Yeah, that's pretty close to pi. It's not exact, but it can't be because you approximated. Let's do it in degrees. It's approximately 36.34 degrees plus 117.28 degrees plus 26.38 degrees. That is equal to 180 degrees. Yeah, that checks out. Maybe I'll point something out, though. If that had been instead 180.01, that still would have been okay. Because we rounded these, and the rounding may not have all been in the right direction for all of the rounding errors to cancel out. But yeah, I believe that these are right. If you really want to know, well, then you can use a machine. So this will be exactly equal to cosine inverse of 29 over 36 plus cosine inverse of negative 11 over 24 plus cosine inverse of negative 43 over 48. and you'll have a machine compute that, and you'll see that, yeah, that is all of the digits of pi that you would want, because the computer will save all of the digits that it wants to. You've only saved, well, I only saved, looks like up to the hundredths place in radians. Nice. So, if you want to solve a triangle, here's how to do it. So the last thing I'm going to do in this note packet is a few applications. I'm going to think about some particular, well, maybe I should say in quote, real-world applications. So I'll mention them now, and I stop the video, and then we'll come and do them in part 3 of this series. While walking in the woods with Robert Frost, you come to a fork in the road. Robert Frost takes the path less traveled by, you take the path more traveled by. Two paths diverge at an angle of 45 degrees. If you walk at a rate of 4 miles per hour while Robert Frost maintains a pace of 3 miles per hour, he's slower than you, right? He's taking the path less traveled by, which has path maintenance issues, which is why it's less traveled by. So he's slower than you. What's the distance between the two of you after 1 hour? Or, let's say you travel due east 3 miles, you then turn 30 degrees to the north, you travel 1 mile further. How far are you from your starting point? So, both of these seem pretty contrived, but this is the mathematics that lets you keep track of distances between points when you know only some information about distances between different points and some angles between them. So this is how, say, triangulation works to measure distances to ships offshore. So let's stop. We'll come back in a bit. Talk to you in the next one. See ya.